Okay, we'll get started. Hello and welcome to the first Plato-Madison lecture for the 2021-22 season. The lectures this fall will be held virtually due to ongoing concerns over the COVID-19 variants. This lecture is being recorded and will be linked to the Plato-Madison website. I'm Joy Cardine. I'm a member of Plato-Madison. I'm a volunteer on the lectures committee, and I'm also a retired Wisconsin Public Radio talk show host. And I'm very pleased to be your moderator for today's lecture, Ask a Weather Guy. The weather guy is Jonathan Martin. He is a professor in the UW-Madison Department of Atmospheric and Oceanic Sciences. He is one of the two weather guys, the other being Professor Steve Ackerman, heard monthly on Wisconsin Public Radio, a very popular segment on the Larry Mueller Show. He is also one of the writers of the Ask the Weather Guys column in the Wisconsin State Journal. Today, which happens to be the first full day of fall, the fall equinox arrived yesterday at 2:20 Central Time. We will learn more about weather and climate. We asked Professor Martin to address climate change in particular, but we also want to give you the opportunity to ask about anything weather or climate related, including extreme weather, heat, storms, drought, our fall and winter weather outlooks, whatever the case may be, whatever weather and climate questions are on your mind. Type those questions in the Q&A section and I will present them to Professor Martin after his talk. Jonathan Martin's research expertise is in mid-latitude weather systems. Over his career, he has authored more than 70 scientific papers, as well as the leading textbook on mid-latitude atmospheric dynamics. He is also the author of the newish book, Reginald Sutcliffe and the Invention of Modern Weather System Science. Professor Martin has received numerous accolades and excellence in teaching awards. He was also named by Princeton Review as among the best 300 professors in the nation. We are very happy to have him with us. Thank you, Professor Martin. Take it away.
Thank you, Joy. I'm going to start by sharing my screen so we can get right to the, well, who can share? Why do I have to answer this? I guess we'll do this. Okay. So I want to share my screen. I've gotten a series of slides together for you all today, and thank you for inviting me. First of all, it's a real pleasure to be here. And I wish we were together, but we'll more than muddle through. It'll be exciting, I think, to talk about what's coming in the wintertime, my favorite season, as Joy pointed out, the very first full day of the autumn, which we're all enjoying together. And I think that's what you can say about the beginning of autumn. You can always enjoy it. So I want to talk today about some of the basic physical elements of the climate change science debate. And so we'll go through some of the issues that are related to what is the physical forcing for changes in the climate system, especially those that we're experiencing right now. And then also, what are some of the questions that are posed by these changes and what can we do about some of them? So we live on a beautiful planet. All of us, of course, only know this planet. We can't really compare it to other ones, but I don't think you'd even need to compare it. When you look at a picture like this, you say, that looks like a pretty fine place to live. It looks like there's vegetated land. It looks like there's beautiful something liquid in the oceans. It turns out to be water. What could be better? And there's clouds and ice evident in this picture. I think you can, maybe you can't see my cursor, but up here on the just under the top of the picture, there's Greenland. So that's under ice and then some polar ice. So there's all kinds of things going on in any one of these pictures at any moment. And across this globe, especially at the middle and high latitudes, there's a parade of weather systems. And I'm just showing you a 10-day animation. This is at 3 hours. It's going fast. I'm not supposed to point out any particular feature here, and I hope that you don't. But what I'm hoping is over the minute or so I talk about this, you get kind of mesmerized by the patterns that you see and recognize that our planet in its atmosphere is exceptionally active. There's things going on every moment of the day, every day. And once you start to view this thing a few times, you can kind of see some broad scale patterns that emerge. One of them is at both the middle latitudes of the northern hemisphere across the continental United States as a guide, and the middle latitudes of the southern hemisphere, you see these swirlies, almost like you poured cream into your coffee cup and stirred it. And those swirlies have a tendency to move from the western side of the diagram to the eastern side of the diagram. Those are mid-latitude weather systems in both hemispheres. They do a lot of mixing of warm air from the tropics and cooler air at the higher latitude polar regions in both hemispheres. Then right at the equator of this map, you can see these pulses of whiteness that are cloud structures coming across the continent of Africa, the northern part of South America, the maritime continent of Indonesia, and the Pacific. And those are convective storms, thunderstorms. We get things like them in the summertime here, but they're very common almost all the way through the year in the tropical latitudes. So that's pulsating, and you can notice that some of those individual clouds are moving from east to west. So the whole flow of the atmosphere is different in the tropics than it is in the extratropics. And what's remarkable is that all of this apparent chaos, even though we're beginning to discern a little bit of a pattern out of that chaos, all of this is governed by rigid physical laws. And those physical laws can be interrogated, tested, measured against in order to determine what is going on both with our day-to-day weather as well as what's going on with the climate system over the long haul. Now, the day-to-day weather, and this is a picture of a parade of weather systems, the day-to-day weather is determined almost exclusively by the initial conditions. The conditions around the globe yesterday have a first-order impact on the weather everywhere around the globe today. So we call that an initial value problem, and the weather is definitely an initial value problem. Similarly, the Brewers have stumbled here this week against the Cardinals. Today, we have another chance. It's an initial value problem. There's no long-term reason to get nervous that our team is suddenly not going to be as good as it has been all summer. They've hit a bump in the road, and it's been a series of matchups that have gone wrong for them and so on. Those are all initial value issues, not conditions that cause you to get nervous. The climate system is not an initial value problem. It's a boundary value problem. And this means that the very largest scales control, and the boundaries of those scales control the behavior of this system. Before I talk about the climate system, I'll use the baseball analogy a little bit more. The Brewers have not recently had tough times at home because suddenly we've lengthened the base paths from 90 feet to 93 feet. And for some reason, they haven't been able to beat out infield singles. That would be a boundary value change to the game that would drastically affect the long-term statistics of it, the climate of it. But that's not what's going on in the day-to-day wins and losses in a baseball season. The same way, that's not what's going on in the day-to-day vicissitudes of the weather. But for the climate, any little change on these boundaries, of analogously lengthening or shortening the baselines in a baseball field, will change the nature of the statistics of the game for a long, long time. Some of the boundary issues for the climate system are, one can say that the long-term average of the climate system is determined by how much radiation, how much energy is actually emitted by the sun. We can measure that. We have satellites out in space that do that to a very high degree of accuracy. How fast does the Earth rotate on its axis? That determines how long a day is. And within a day, right around now, we're looking at about 12 hours of sunlight per day and 12 hours of darkness. But that won't be the case all the way through the season. And that has to do with the orbital characteristics of the Earth. It's tilted on its axis and it orbits around the sun in an almost circle, but it's actually ellipsoidal. And so 3 months from now, of course, we'll enjoy a very late sunrise and a very early sunset compared to what we experienced just a couple of months ago. And then a final boundary issue is the composition of the Earth's atmosphere. It's not one gas only. It's maybe easy to believe that it's just mixed up one or two primary gases. It's not true. There's a whole bunch of different gases in the Earth's atmosphere. Primarily, it's nitrogen and it's molecular nitrogen and molecular oxygen, which thank God we wouldn't be talking to each other today were that not the case. But there's a whole host of other chemicals. And some of those chemicals have some quite peculiar properties with respect to the whole spectrum of electromagnetic radiation. One type of which comes from the sun, another type of which comes from our bodies because we have a temperature above 0 Kelvin. And so a number of different chemical constituents in our atmosphere have the characteristic that they're transparent to solar radiation, just like the windows, which I hope you have access to on a beautiful fall day like today. All the visible radiation from the sun is coming right through those windows. But those gases can also be translucent. That is maybe like a dirty window to infrared radiation, which is the kind you and I are emitting and the kind the surface of the planet and its atmosphere are emitting at all times. Gases that have that combination of characteristics are known as greenhouse gases. And I've listed a few of them that exist in the Earth's atmosphere naturally here on the left-hand side of the diagram. Methane is one, water vapor is one, carbon dioxide is one. I want to say a word about the nature of these diagrams. The bottom axis is at the bottom of the page. You might see it, and that's wavelengths in millionths of a meter. So the far right extreme is 20 millionths of a meter. That's about the radius or the diameter of a typical raindrop. That's about how big 20 microns is. And then all the way on the left-hand side, you get down to 0.1 microns, which is, one much, much smaller than the 20 microns. And then on the y-axis is the fraction of energy in that wavelength that's absorbed by the chemical in question. So look at the methane chart. There's two big spikes of absorption where the yellow shading goes almost all the way up to 100% absorption. One of them is at about 4 or 3.8 microns wavelength. The other one's at about 6. Then the next gas is water vapor, invisible water gas, not steam, invisible water gas. And that has a huge amount of absorption going on across a wide variety of wavelengths, sometimes approaching 100%, other times hovering around 50%, such as in the band from about 15 to 20 microns of wavelength. And then there's carbon dioxide, which has two spikes. One of them is coincident almost with the methane spike at about 3 or so microns. The other one's closer to 4.5 or something like that. And then when you get to the so-called really far infrared, 15 to 20, the atmosphere is effectively a brick wall to that radiation leaving the atmosphere because of the presence of carbon dioxide. So every one of these chemicals, and I've only listed 3, has its own unique universal signature. No matter where you are in the universe, if you're a methane molecule, you're going to absorb radiation of this type at this intensity or absorption percentage, no matter where you happen to be in the universe. And so these are like the fingerprints of these gases. And our atmosphere happens to have several such gases that are very good at absorbing what would otherwise be outgoing, that is from the ground to space, infrared radiation. If you add up all of them, because there's more than 3, this is the bottom picture, gives you the total atmospheric absorption spectra. Where along this spectrum of wavelengths is the atmosphere's presence absorbing radiation? It almost absorbs nothing in the visible. That's the yellow shading on the far left from about 0.4 to about 0.8 microns. That's the kind of radiation that you and I can see with our eyes. And so we're sensitive to that. That's very short wavelength, high energy radiation, but it's the visible spectrum from the sun. Almost none of the visible light emitted by the sun is absorbed by the presence of the atmosphere. As you can see, there's just a little hump there at about 0.5. And in fact, the sun emits 44% of all of its energy in those wavelengths. So we have a really nice relationship with the sun in terms of it's sending its majority of radiation in those wavelengths, and our atmosphere is completely transparent to them like a window. Then the Earth emits most of its energy because of its temperature from about 0.7 to about 11 or so microns. And that is also largely an empty window, a clear window, as you can see, but it's not entirely clean. And so the little bit of dirt on that window prohibits some of that radiation from leaving the planet, and that stays back behind keeps us warmer than we have a right to expect at 93 million miles away from a sun that emits a certain amount, which we know, of energy. Okay, so we should be a lot colder than we are. The average temperature of the planet, were it just a bald rock in space, 93 million miles from the sun, would be 0 degrees Fahrenheit. The actual average temperature of the Earth is 59 degrees Fahrenheit, and that crosses a critical threshold, which is the melting point, freezing point, if you want, of the water substance. If we don't have liquid water, we don't have life. So the presence of these gases ensures that the planet is warmer than it has a right to be at the distance that it happens to be away from the sun. So here's how that works. All of the radiation that charges the whole system comes from above the clouds, comes from outside the atmosphere, that is from the sun. So let's say you got 100 units of energy coming from the sun per second. Some fraction of those 100 will simply be reflected either by the surface of the planet, like over a water surface or over a sandy surface, and the reflection fraction will be different depending on the nature of the surface. So some of the solar radiation will be reflected by the Earth itself. Some of it will be reflected by the atmosphere and items that happen to be there, like clouds or something. The fraction that is not reflected away back to space gets all the way through the atmosphere, because the atmosphere is transparent to solar radiation, and it is absorbed by the surface of the planet. By that, I mean everything. I mean the oceans, the trees, land, no matter what it is. That radiation gets absorbed by the surface of the Earth, use the word surface broadly, and it warms up the surface. And as soon as an object has an increase in temperature and absorption of radiation, that object begins to emit its own radiation. And the type of radiation emitted by an object depends upon the object's temperature. And at terrestrial temperatures, including our body temperature, temperature of the grass outside in the backyard, whatever it might be, those are all going to be emitting in the infrared wavelengths because of their relatively low temperatures. And so there goes the infrared energy escaping hotly out to space. But there's an atmosphere between the surface of the planet and outer space. And that atmosphere, as you can see on the left-hand side of the diagram, is very good at reabsorbing some of that outgoing infrared radiation. And so, as I say, some of that outgoing infrared radiation never escapes. It gets reabsorbed by the various gases in the atmosphere, including water vapor, carbon dioxide, and methane. And then those gases, once they've absorbed the energy, they must re-emit it in every direction. And half of those directions point back to the surface. That's indicated by the green arrow. And so that accounts for a retention of infrared radiation that would otherwise escape to space and cool us off. It's retained by the presence of these greenhouse gases, and it's added as an additional input of energy to the surface of the planet. And the only way it can balance is the planet has to warm up in response to that retention of infrared energy. So that's how the greenhouse system works. And we have a naturally occurring greenhouse on Earth, as I mentioned before. We would never expect liquid water on this planet, given all of the cosmological values of the output of energy from the sun, the distance we are from the Earth, from the sun. But it's because of the chemical composition of the atmosphere that we have the ability to be warmer than the freezing point of water. But as you might guess, some of the chemical concentrations of those important greenhouse gases are not constant. They don't stay at the same value forever. They go up and down. In some cases, they go up and down over extraordinarily long periods of time. This is the carbon dioxide concentration reconstructed from ice bubbles, in bubbles of air in ice that you can get from these extraordinarily long ice cores down in the South Pole. And so anybody who's ever skated on the lakes around Madison or even walked across them, you realize when you walk on a sheet of ice that's naturally occurring, there's going to be little air bubbles. And those air bubbles, it stands to reason, have the exact same chemical composition of the air inside those bubbles as the air that's out in your atmosphere on that same day. And so the principle is very simple. If you can determine that the ice that you've drilled at a 6-mile depth or something is 400,000 years old, and you have careful chemical composition measurement devices in a laboratory, and you have experts doing it, you can see what the air's composition is 400,000 years ago. And among other things, you might want to measure what the carbon dioxide concentration was 400,000 years ago by that proxy. And apparently it was around 280 or so parts per million. That is 280 molecules for every million at random were carbon dioxide at that time. And then you'll notice 100,000 or 50,000 years later, it had dipped down to something like 190. So not as much carbon dioxide. That means not as much retention of infrared energy from the surface of the planet. Planet's cooler then, probably. And then it spiked to 300 about 25,000 years later, and so on. You can see these up and down. Sometimes they're 50,000, 20,000 year long periods, sometimes more like 100,000. And so this is the proxy data that we can use to get an estimate, and it's a really good estimate, of how much these trace gas concentrations have changed over time. And over this period of time, this is, predating massive industrial civilization. So this is what happens in the natural background on the planet Earth, or at least has in the last 500,000 or so years. You can use other proxies to look at more proximate time series of these concentrations of these gases. So these will include maybe tree rings, diatoms from the ocean, various other closer in time and therefore a little bit more accurate things to read, perhaps. But you can look at more than one species. And here we're looking at carbon dioxide in red, methane in blue, and nitrous oxide, laughing gas, is also a greenhouse gas, and that's in black. And you can see over the last 2,000 or so years, those gases have all had a fairly constant concentration from 2,000 years ago up to about 1750 to 1800. And then suddenly they go skyrocketing up towards the current really high values, which we'll talk about in just a minute. And so all of these greenhouse gases are increasing in concentration, and the increase has occurred over the last 150 or so years, very dramatically. And that is circumstantially tied, of course, to industrialization. Here is an even higher resolution and therefore even more certainly correct measurement of the carbon dioxide concentration of the Earth's atmosphere. This is measured, this is started by Charles Keeling in 1957, and his son Ralph continues it now on the top of Mauna Loa, which is about 10,000 feet above sea level in the middle of the Pacific Basin. So it's fairly pristine. It's out of the industrial boundary layer of the Earth's atmosphere. And this gives us a really good indication of what the carbon dioxide concentration actually is in the Earth's atmosphere. So at around 1957, you see the red line is the daily time series, and then the black line is the average of that. And the daily one has ups and downs because it's in the northern hemisphere. When the northern hemisphere greens out in the spring, it actually draws down carbon dioxide for the vegetation to grow. And then when it falls out like it's doing now, the carbon dioxide concentration will go back up because there's nothing pulling it back out in the growth process. So that's the up and downs in the red. But the long-term trend, of course, is scary. It's gone way, way up from about 318 or so parts per million, which is, quite like what it was in the longer time series from the Vostok ice core at its peak. It's around 300 or so, but it's gone all the way up to the current week. We're at 413.43, I think, parts per million or something like that. You can look this up every day if you'd like. So this is really scary. That's an increase of about 100 or so parts per million above anything we've seen in the last 800,000 years. We've never seen this kind of carbon dioxide concentration measured by proxies or measured directly in the last about 1 million years, at least, perhaps longer than that. And this is a direct measurement that we're taking every day in Hawaii. The largest amount of the increases in carbon dioxide has come from the burning of fossil fuels. And this is not just an assertion. This is a fact that can be determined by the consequence of fossil fuels are a global industry. Nobody guesses at how much they've extracted from the earth. Nobody guesses at how much they've sold to the Strategic Petroleum Reserve or how much they've sold into the actual market that's burning it. So we know all of those numbers. Those numbers are not a mystery. And it turns out also that atmospheric carbon dioxide has roughly tracked the rate of growth of fossil fuel consumption. Again, not a guess that's made on that second part because it's a global business. And the atmospheric carbon dioxide is several parts per million higher in the northern hemisphere, where the largest cities are, where the largest populations are, and so on. So that's all really interesting. To me, the hand-to-glove piece of evidence that just makes it beyond dispute is the last one here. And that is that the atmospheric molecular oxygen reservoir, which is in no danger of being depleted. We have 22% of every breath we take is molecular oxygen. That's a lot. It's decreasing at 3 molecules per million per year, which is consistent exactly with the addition of carbon dioxide by combustion of fossil fuels. So this is a glove fitting the hand. There's no way to argue that point. Okay, so that's pretty strong evidence for where the extra carbon dioxide is actually coming from in our atmosphere. And when you take a look now at some of the consequences of that increase in carbon dioxide, recalling, of course, that the more carbon dioxide there is, the more retention of infrared radiation that would otherwise escape to space will be accomplished. That means the planet stays warmer with a higher carbon dioxide concentration. And this has, of course, happened even in the remote past. There's no reason why those physics are not going to work in the current day. Here's the last 150 or so years of global average temperature from 5 different sources. Now, they all use probably many of the same instrumental records, but they do their own sort of analysis of the instrumental record, and they do that independently. And then when you throw all 5 of these different independent assessments of that long-term instrumental record and its problems and biases and its corrections that need to be made, all done by different groups in different ways, you get a remarkably consistent picture of what's happened over the last 150 years for the global average temperature at sea level. And so we see that, first of all, the increase has not been uniform in one direction only with a constant slope. From 1880 to about 1920, there was not much change at all. Then from 1920 to about the beginning of World War II, there was a fairly rapid increase, almost it looks like the increase rate that we have currently. And then from the war all the way to about 1980, maybe 1975, it looks like a sort of a flat trend. And then from about 1978, 9, 80, all the way to the current day, it's a very steep increase. Again, I think it's at least as steep, perhaps a little steeper even than the 1920 to 1940 increase. Now, part of the reason is I was going to put some extra stuff on this diagram, but I'll just talk about it instead. 1880 to 1920 was a period of global volcanism, as was 1940 to about 1960, 1970. And so volcanoes emit aerosols because they have this big explosion of ash and dust and so on. And that serves as a shield for incoming solar radiation. And if you reduce the solar radiation input by a little bit, as a consequence of volcanism, you're going to have a decrease in the global average temperature. And if you have a particularly active period of volcanism, then it's really hard to shed and have that ash rain out and get you back to something that's more normal. So people have theorized that this trace actually shows a sort of occasionally thwarted rate of increase, thwarted, that is, by the presence of ash and dust from volcanoes. Were that not the case, this rate would have been nearly constant over much of this period of time, is one of the theories. So that's kind of one way to think about this. Let's go back to the top diagram. Here is the carbon dioxide concentration as measured from bubbles in the ice from the Vostok ice core. And then you can also make, I don't know how, it's not my specialty, but you can also make estimates by other isotopes of chemicals about what the average temperature was. And then you can look at in those remote times and then compare it to what the average temperature is now. And so you get a difference in temperature change from present on the bottom diagram in blue. And you'll notice that every time the concentration of carbon dioxide goes down, so does the global average temperature. When it goes back up, the temperature goes back up, and so on. These diagrams do not sit perfectly on top of each other. That's not the only factor. But on very long time scales, it sure looks like a primary factor. Global average temperature follows atmospheric carbon dioxide concentrations. That is very difficult to argue with. There are other ways to assess whether or not changes have been occurring in a systematic way. One of them was a really ingenious study by John Magnuson, who is part of the limnology program here at the University of Wisconsin-Madison. John and his colleagues looked at more than 38 sites. They actually had maybe twice that many over the Northern Hemisphere with time series that went from mid-1840s to about the mid-1990s, so about 150 time series. These were all of lakes that had a history of somebody recording the ice on and the ice off dates. And so first they assembled their nearly 70 or 80 lakes across the Northern Hemisphere. Then they decided, let's make sure we're not biasing a certain region, make these as uniform as possible over the land masses at high latitudes in the Northern Hemisphere. And that's how they settled on the 38 that they used, just so that it was not regionally biased. And it turns out that over this 150-year period, the ice was coming on about 8.7 days later, and it was being thawed and melted away by the local measures about 9.8, nearly 10 days earlier than it used to. So that's about 18 days of difference, shrinking of the ice, the length of the ice season from 1850 to 1990. And 18 days represents about 20% of the average season on Lake Mendota. So here's the Lake Mendota time series. The black line is every individual year connected from one to the next. And you can see there's an extraordinary amount of interannual, that is between years, variability. When you put a 5-year running average on there, that's the red line. And you can see that makes it even more obvious to the eye, at least, that there's a systematic decrease in the length of time the ice stays on Lake Mendota. And we don't change the rules about how we measure that length of time. It has to, I think you got to have continuous ice from Picnic Point to Governor's Island or something like that. And or when it melts away, there's got to be gaps in that. So that's, I think, the measure. Don't quote me on that. I may be wrong. It's not my field, but I've heard it's something like that. So, but the important point is the rules don't change. And so the lake is not carrying ice for as long as it used to. That's really hard to argue that there's something up in the wintertime when that's the case, especially when the Magnuson et al. Paper says this is true at 38 disparate sites across the Northern Hemisphere over the same period of time. So it kind of gets us headed towards talking about the winter, and that's really my favorite season. I love the winter. I grew up in northeastern Massachusetts. I had a morning paper as a boy. I was a young man. No, I wasn't even a young man. I was a young boy when Neil Armstrong walked on the moon for the first time. So, I had all of these senses of adventure and whatnot, making footprints in dusty substances in my head when I first got my paper 2 years after Armstrong was on the moon. And there I was walking through New England snowstorms in the morning before anybody else was out there, and making the same sort of sense of, discovery and adventure that I imagined he must have felt while he was on the moon. So I've always loved the winter. But sometimes the winter is boring where you happen to live. I was a graduate student in Seattle, Washington for 8 years, and it never snows at sea level. And my friends and colleagues there would say, John, stop complaining about that. All you have to do is go up to the mountains. And I said, no, you don't understand. You want to see what your normal life is like when it's crippled by snow. It's not the same to visit a remote place where it snows. So I couldn't make that deal with people. They couldn't understand me. But here in Madison, sometimes we get a pretty good amount of snow in the winter times, but other years we don't. This particular year, 2011 and 12, we were in a snow drought. In fact, it wasn't even cold. It was a really boring winter for us. Meanwhile, headlines from Alaska, one of the coldest winters they had in some years. It snowed in Morocco. It was snowing in Rome. I was furious. And I decided I have got to figure out a way to enjoy the depths and the intensity of winter remotely, even if it's not happening where I live. And I thought, how can I do that? So long story short, I decided to start keeping track of the aerial extent of air that was colder than -5 degrees Celsius, which is 23 Fahrenheit, at a pressure level 850 millibars, which is roughly a mile above the surface of the earth in most locations. So this is what it looked like at noontime London time on the 2nd of February, 2012. The blue line on the outside of this shaded region is the -5 degree isotherm, line of constant temperature. And then the shaded area is the region where it's at least that cold or colder over the northern hemisphere. And it occurred to me, it's not so hard to calculate the area of that shaded region. We have gridded data sets at 1 degree latitude, longitude resolution. It's quite easy to actually write a little program that does this for you. So I started to calculate the aerial extent of the 850 millibar cold pool, I called it. And this is just one day. One time, actually, I get 4 times like this per day. And then I have a data set that goes all the way back to January 1st, 1948. So I can look at 73 now seasons, December, January, and February only, cold seasons in the Northern Hemisphere, and see how this aerial extent expands and contracts during the season. And in a long time series, is there any trend in it? So here's a whole bunch of fun things you can do with that. This is a diagram that actually just shows the aerial extent of the air at -5 is the biggest hump, and then -10, 15, 20, and 25. So different thresholds, but the -5 is the one we'll concentrate on. And it grows enormously from the end of July until the middle of January. And then it shrinks back down at the same rate from the middle of January back to July. So these are beautiful sinusoids, all of them. And this is perfectly sensible. This just testifies to the fact that when you head towards the winter, and we're headed there now, we have a shorter day today than we do at night. When you head towards the winter, the aerial extent of this cold air expands until it reaches its maximum about a month after the solstice. And then it shrinks again. And it doesn't matter what threshold you pick, nor does it matter, how long the time series is. This is the way it looks, beautifully sinusoidal. But that's not the most interesting thing that you can do with it. You can take, as I mentioned a minute ago, I get 4 such aerial pictures like that one every single day. And then I have 73 seasons of 90 days, December, January, February. I don't count leap days. And so every one of these dots on the top line, on the far left, that first red dot represents 360 calculations of the aerial extent of cold air for the December, January, February, 1948, 1949, condensed into one average value for the season. And then the next red dot is the same thing for the next season, and so on. Then I have 2 other data sets. I'm using one of them is the so-called National Center for Environmental Prediction reanalysis. That's in red. The other in blue is the European Center reanalysis. That's a 40-year reanalysis. And then the green is a newer product also from the National Centers for Environmental Prediction, but at a higher resolution. And that's in green, the so-called CFSR. You can see that at every one of the thresholds, the top one is the -5, and the others are there as well. At every one of the thresholds, these 3 data sets measure this characteristic quite similarly. In fact, almost perfectly the same. And that's not surprising. It's such a basic measurement. But look what's happened from 1948-49 to the present day. The last one is the 2021 wintertime. We went from about 70 or so million square kilometers for the average horizontal extent of the cold air in 1948-49 to something closer to like 66 in 2021. And that decrease has not been uniform, but it's been pretty systematic. In fact, the trend line is the black line through all of those dots. And those trends are significant at the 99.9% level, which means there's about a 1 in 1,000 chance that this would have happened by accident and that there's not something forcing this systematic downward decrease. And it's true at every single threshold. that you show on this diagram. So the aerial extent of cold air in the wintertime in the Northern Hemisphere is shrinking, and it's demonstrably shrinking and systematically shrinking. Really interesting to me. Remember a few years ago, we had an exceptional cold wave, late January, early February. That was 2019. So here's the daily time series in red of the aerial extent of the -5 air at 850 from this winter, December 2018 through February 2019. A note about what's on there in addition to the red line. The blue line is the calendar day average for every single day in that 90-day cold season. And then the gray shading above and below that blue average line is plus and minus 1 standard deviation. So how frequently does the value exceed or find itself below the daily average at 1 standard deviation? I think there's about 66% of all days will fall in between the shading if the statistics hold. So here's where we had our near record cold here over the Great Lakes, really exceptionally cold last couple of days of January. Notice at the same time, the hemisphere was almost 1 standard deviation smaller than average for its aerial extent, which indicates, of course, that the hemisphere was warmer than usual on that day, but not so locally. So there's the disconnect between weather and climate. And people use this sometimes to promote their skepticism or to patch over their skepticism about climate change. It's easy to say if it snows in Brussels or something, which is unusual, hey, how can the climate be warming? That's crazy, because when we were minus 30 degrees here in Madison, the hemisphere was warmer than usual by quite a distance, or quite an amount. But here's really something that's also cool. Now I'm adding to the gray shading in the blue line as the average, I'm adding the extremes. So the little thin blue lines that go up and down in this diagram indicate the extremes for each calendar day over the 73-year time series. And then I've got 2 different annual time series. The first one's 1971-72, and the other is 2013-14. I think I can't read it because the boxes of, on Zoom is kind of clouding it over. But anyway, the point is, notice in 1972, right about the time President Nixon was walking the Great Wall of China, and I was seeing that in the newspapers because I was delivering them. That winter was my first winter. You had a really cold hemisphere. The hemispheric aerial extent of cold air was at least twice 2 standard deviations above the daily average for February 1st, 2nd, and 3rd. And then in the winter of 2013-14, we had more than a few days where we had an aerial extent. Here's one that I highlighted in the pink dot, or at the end of December, which was 2 standard deviations smaller than the average for that calendar day. So I'm going to call such days as when you have 2 standard deviations below the average aerial extent an extreme warm day, and days where you have 2 standard deviations above the daily average as an extreme cold day for the hemisphere. And look at this. On the left are the 2 sigma cold events. The extreme cold days on the right are the 2 sigma warm events. And this is a subset of my total data set, 1948-49 to 2013-14. All of the cold events are front-loaded in the time series. In fact, the last one we've ever experienced was a week or so before I interviewed for the job that I currently have at the University of Wisconsin. And this is my 28th year in that job. And then all the warm events, they're kind of spread out, not quite evenly, but they existed occasionally in the early decades, but they've really increased in their frequency in recent decades. In fact, when you put some numbers to this, and I'll go beyond 2013-14 here in a minute, there have been 117 days that qualify in the long time series as extreme cold events. Not a single one has occurred since the 13th of February, 1994. 253, is it? I can't remember what the number is on that. 251 days qualify as extreme warm days, 168 of them since the year 2000. So something's up. This is not a fair die anymore. When you're throwing dice, it's not fair. You expect it's going to be a warm event, extreme warm than extreme cold. Oh, I don't know what happened here. Okay. What's the matter? Okay, so some conclusions about what we found here. Over the last 72 years, and 73rd year is being compiled right now, the aerial extent of the Northern Hemisphere wintertime cold pool, temperature -5 at 850, has decreased by 4.56%. That doesn't sound like much, but when you have the central pressure of a cyclone go from its standard sea level pressure to 4.5% below it, you're in the middle of a Category 3 hurricane. The atmosphere does not tolerate departures from average very well without drama. Okay, so that's definitely a substantial change. The shrinking cold area is definitely a result of greenhouse warming. because the only way you can erode the cold at the edge of that boundary systematically is to retain more infrared radiation in the atmosphere and warm it up as a consequence. There's no other way to explain that. Extreme cold events have effectively stopped happening the way I define them, while extreme warm events continue on. In fact, the score since February 1994 is 205 warm to 0 cold. Now, anybody who's a sports person has played any game at all, if you're losing a game 205 to nothing, you probably are discouraged from playing ever again. And I think we are never going to see what we called in the recent past an extreme cold event by this somewhat arcane measure. They just don't happen anymore. Unbelievable, isn't it? But scientists are a skeptical bunch. I had a hard time getting this little paper through, but imagine trying to convince people of a broader problem than just this little thing. But let me say, the skepticism is something we can use to our advantage in terms of feeling confident about the results. In 1995, the Intergovernmental Panel on Climate Change released its second assessment. I forget when they met the first time. It must have been 1989 or something. And in their second assessment, at a point in the document where they make a statement about whether or not human beings have had anything to do with the changes that we were seeing up through 1995, they made this rather vanilla statement. The balance of evidence suggests that there is a discernible human influence on global climate. That's pretty vanilla. They knew right away that wasn't going to work because more refined observations and analyses were brought to bear in the run up to the next assessment. Before they made that assessment, they knew they had to do something which none of us should ever have to do. This is part of Dante's circles of hell. That is, serve on an adverb committee. They had to determine ahead of time what adverbial phrases and adverbs themselves were going to mean when they were used in subsequent reports. So can you imagine? This is true. I'm not making this up. Likelihood scale used in the reports that were subsequent to the 1995 one. And you can see it all. Likely was going to mean there's a 66 to 100% probability. Very likely 90% or greater. Extremely likely 95 and so on. Okay. So they had to set these rules before they used these words. So after more refined observations and analysis, 5 years and 6 years later, the third assessment comes out. Most of the observed warming over the last 50 years is likely to have been due to the increase in greenhouse gas concentrations. Likely, 66 or greater percent probability. Still, not a gung-ho statement. More refined observations and analysis, 6 years later, the fourth assessment comes out. Most of the increase in globally average temperatures since the mid-20th century is very likely due to the observed increase in anthropogenic greenhouse gas concentrations. That's now, I'm sorry to do this again, I want to just make sure I'm right. Very likely is 90% or greater probability. And then more refined observations and analyses. We don't stop thinking about this problem. 6 years later, in the fifth assessment, it is extremely likely, 95+% probability that human influence has been the dominant cause of the observed warming since the mid-20th century. Just last week or 2 weeks ago, the IPCC's sixth assessment came out in this 2021. It is unequivocal that human influence has warmed the atmosphere, ocean, and land. The scale of recent changes across the climate system and the present state of that system are unprecedented over many centuries to many thousands of years. This is no longer a vanilla statement. This is a pretty solid statement of unequivocal conclusion that human beings and our activities have changed the nature of the climate on Earth. We know how they've changed it. We know why those changes have been wrought. The questions now really ought to be, what can we do about it? And how can we organize ourselves as a species across cultures, across nations to make things better? So that's the question that I have. And I thank you for your attention, and I'm happy to take any questions that you might have. And should I stop sharing the screen, Joy?
Yes, please.
Okay.
Then we can see you a little bit better.
Okay.
And yeah, thank you so much for the explanation, the elements, the evidence of climate change. If you have a question for Professor Martin on climate change, on global warming, or if you have another weather or climate related question, we have a Q&A box just for you. You can type your question in Q&A and I will pass it along to Professor Martin. I'd like to just start with I mean, that was amazing to see how that moved from, well, maybe, human activity is related to, it is unequivocal that this is due to human activity. What if nothing, is done, Professor Martin, to mitigate, to prevent, to reduce the greenhouse gases? What happens?
I suppose that's a great question, Joy. I suppose and now we're trying to use numerical models, the same kind that we use to predict the weather from day to day, but with different types of implementations of the relationships in nature as massaged into mathematical expressions. But the success of numerical weather prediction is undeniable. People can, I think, accurately characterize the weather out 6 to 10 days with adverbs that are not really far off. The actual details might be a little bit off. And I think the same thing is true with that same type of technology for making climate assessments into the future. And so climate models are one way that you can actually answer those questions. What will happen if we don't do anything? And the IPCC often does run several different simulations. They put it in their executive summary. One of them is called the business as usual scenario. And they run a model as if we do nothing to change our carbon dioxide output and various other greenhouse gases, do nothing to change the way we power our economies. And that always invariably is the one that shows the greatest rate of increase of global average temperature. And I think in the current one, we're talking about an increase on the order of 8 or so degrees Celsius over the next 50 years if we have business as usual. And remember, we've just seen about 1.2 or 3 degrees over the last 150 years as we've begun to really spin this problem up. So it's going to increase in the dire nature of it much more rapidly than it has in the lifetimes of everybody who's viewing this currently. And that's kind of scary. Another way to do it, more simple-minded, is to just think about the Mauna Loa carbon dioxide trace. I remember seeing that thing. It was about 15 years old when I started college as an undergraduate. And I remember thinking, wow, we've had a pretty big increase from 1957 to 1982. And that has not been linear. It's gone up even faster. And so if you keep on drawing a slightly exponential curve for the next 50 years, you put us at something like 550 or so parts per million as business as usual. We can't afford that. The planet, this is one thing that drives me nuts. People say the planet won't survive. No, that's parochial. The planet will survive. The planet's been hit by asteroids. It'll survive. Human civilization is what's at risk, not the planet. But maybe that's what people mean when they say that.
A question from one of our attendees referring to the weather report on television news, one of the most followed. What movement might you be aware of, Professor Martin, amongst meteorologists to incorporate climate change awareness in their reports?
That is a good question. I'm aware now that some of the big names across the country, Tom Skilling is one. And Tom Skilling's fought, I've met him a few times, know him a little bit. He's fought for over 35 years to expand the WGN weather report to 8 minutes long. I asked him one time, Tom, how in the world did you get granted that? He says, granted is the wrong participle. I earned it because it took years and years of expanding his expertise and encouraging the station to go along with having it lengthened to get him to that point. Tom regularly incorporates statements about, like the IPCC, I think was certainly going to be something he highlighted over a period of a couple of weeks. But when there's an extreme weather event, he does sometimes try to make some statement about whether or not this seems clearly related to the background change in the climate, or whether or not it's just part of the variability that we can expect in the day-to-day weather. And I think those kinds of statements, we got a really intelligent populace in our country, because we're a rich nation. We should be encouraging people's interest and curiosity instead of discouraging it by saying, let's never talk about this. We should talk about it more. And I think we're going to benefit by doing so. Tom Skilling does it. Others, I think, on higher profile, maybe the CNN weather people will do that occasionally. Certainly the Weather Channel tries. But it's not trickled down to every single station. Bob Lindmeier in Madison has been really good about this. He's been a real leader on this, to his credit. And so there's a beginnings of a movement like that, and I think it's great.
Another question, good statistics on weather variability by geography versus climate change. With higher daily temperature records, like in the Northwest this year, can still cause temperature drops in Texas due to the limit of change by the Earth's thermal mass and buffering atmosphere physics. Oh, this is over my head already, but I'm hoping you're following, Professor Martin. So some cold records can still tie 150-year records, but be overtaken by daily highs in other places.
Well, I'm not sure there's a question there. It sounds more like an assertion that is saying that it's an equal chance of having an extreme low or extremely high temperature, and that simply is not the case. Observationally, over the last 50 years, all-time highs have been broken twice as frequently as all-time lows, and that's consistent with this notion that I just showed all of you about the temperature about a mile above sea level, instead of looking just at station observations right at the ground. It is more likely that we are warmer than normal on a given day than it is that we're colder than normal on a given day. That's just a simple fact, and that's consistent with a background warming of the planet. Whether or not every single extreme, especially every single warm extreme, is directly tied to a climate change is a very valid question, because I think we sometimes, broadly, the community attributes too much of the day-to-day extremity in weather to the background climate change. That's not, I think, fair or defensible. But over the long haul, in a conglomeration of the statistics, it's really undeniable that the fact that we're out doing 2-to-1 warm events versus cold events in terms of extremes is that's not an honest balance. There's something going on in the background.
You mentioned when we had that really cold snap, maybe that was the polar vortex, I'm not sure, of like around 2018, 2019, and how some politicians included would say, boy, it's extremely cold out. Where's that global warming everybody's talking about? And dismiss that global warming was an issue, or even say something like, I wish we had some of that now to warm things up a little bit. It's so cold out.
Right.
But also this summer, at least I was, and I don't have the exact statistics, but June and July were in the top 3 hottest months ever, in at least in North America or in the entire world. I'm not sure what August was. But what's the difference there? Can we look at hot weather in the summer and say, see proof of global warming, and then say, well, no, polar vortexes, that's just winter weather that just happened?
Yeah, I think it's dangerous to use regional observations of either extreme, cold or warm, as a harbinger of, as evidence for a global phenomenon. I think that's a dangerous game. I think even the Pacific Northwest heat wave that was extreme, a couple of places in Canada set the all-time national record 3 days in a row. I mean, that never happens. That's unusual. Circumstances were quite unusual there. It was probably partly the background warming that exacerbated what might have been natural tendencies to develop structures and circulations that would lead to those extreme temperatures. I think it's a little premature to say that without global warming, there was no chance of that extreme heat event going on. That may turn out to be true after very careful study, but you can't do that kind of careful study in 2 weeks. So I think when people were saying that in mid-July, that was a little extreme. But on the other hand, Senator Inhofe comes into the Senate chamber with a snowball in February of 2015 and says, where's global warming, like you point out? That's ridiculous. That's just as dumb. And so, you can't look at individual locales and their weather extremes and use that to assess what's going on the global scale. On the other hand, if you look at 15 years of extremes across the entire globe, and that large collection of extremes is biased toward warm extremes, not cold ones, it probably is telling you something that the dice are loaded towards warmer situations. And that's a fair way to make a first order statement about what's going on. So the distinction between climate and weather is fuzzy at the boundary, and people on both sides of the argument use it to or think they're using it to their advantage. They actually anger me because I know what they're doing. And I think most people have a sense of what they're doing. It's trying to cherry pick things that make their argument stronger.
On the other hand, what about we did this summer see continued horrible wildfires all over the West due to drought conditions, in part. We have these violent and strong hurricanes hitting the Gulf every other month, and even the Northeast, the remnants causing horrible flooding on the East Coast. And not, so we have hurricanes and extreme weather and wildfires and flooding. Is that evidence of climate change?
I think certainly the prolonged droughts in certain places that are arid to begin with, the longer they stay arid, the more dangerous the wildfire risk. Also, it's easier to raise the temperature in those locations, so you risk the chance of having extreme high temperatures in addition to the drought and fire risk. Those are all things that I think can be tied to the background climate change, especially those three, because long-term droughts, I mean, interannual droughts that keep on going from over many, many years, are a function of something changing about the circulation of the Earth's atmosphere to make what were already relatively dry spots even drier. That is definitely something on the very large scale, long time scale sort of climate issue. And then anything related to that, drought, like wildfire risk and extreme high temperatures, is tied in. Hurricanes, to the extent that there's increased carbon dioxide radiating energy down to the surface of the planet, and some of that surface is tropical ocean, and that energy is absorbed by the tropical ocean, it does increase what's called the oceanic heat content. And it's a simple-minded idea. How much heat is actually stored in the water in the ocean? So how deep, in other words, does the warm water go? And the deeper it goes, the easier it is for hurricanes to draw that energy into their storms. If it's a shallow warm layer, it doesn't really do much for a hurricane. It'll maybe spin up a little bit of a thunderstorm complex, but if it exhausts all that oceanic heat, it's not going to be sustained. So if we start to see a larger number of intense hurricanes, and those who study this say that's just beginning now to become clear in the data, that would be a signal that's tied to the increased carbon dioxide content of the atmosphere, and indirectly through warming the oceans and deepening that, or increasing that oceanic heat content. So there are connections there that are legitimate. Not every argument that you hear in the press, however, is one of those legitimate arguments. And I think that's where it starts to get a little bit tricky for the person who's the non-expert, but who's very interested in trying to discern who's telling me the truth and who is kind of cherry picking.
Another question: where can we look for signs of hope that we can indeed make the kinds of collective and individual changes we need to make to slow climate change?
How many of us were born before we'd ever set foot on the moon? Probably a large fraction of people. I know I'm one of them. If someone had said in 1920, we're going to put people on the moon by 1970, I think we would have probably said, you're crazy. Why are you wasting my time? Blah, blah, blah. This country can do anything it wants. This country has the greatest human resources, the greatest natural resources that any place has ever had before. What we need to start doing is sifting through what we consider problems and realize what are the real problems. There's no longer a problem in interpreting what's happening with the climate. We know it's warming and we know why. Now the question is, among many different types of solutions, let's have an honest debate. Let's put all of our political energy, and part of that political energy is friction between views, and that's perfectly okay. We need that in our country. But the friction between those views is being wasted on problems that are not problems. It is not true that global warming is a hoax. That is not true. It is true that we need to develop a series of solutions. What are we going to do about it? And we should spend our energy on that. For my money, I'd like the United States to be the first country to figure out how to really use renewable energies in a huge way. I mean, what a great test. We have an enormous economy, a very vibrant economy. Is there a way we can scale up some of these sustainable and renewable energies to power that economy? I'm not suggesting an immediate cessation of the use of fossil fuels, but that should be the background goal. We should be aiming for that. And by marching forward slowly and incrementally, we can do it. But if we keep fighting about things that are not stuff we should be fighting about, we're not going to get there. I think we can do it. Anyway. That's the hope.
I'm gonna switch from climate to weather now and see if you can. Winter is your favorite season, is that right?
Indeed, I love it, Joy. Love the winter.
I love all seasons to some extent, but I have to say I love the other ones a little bit more than winter.
Most
but-
people do. I know I'm in the minority, but I love it.
But what is it? I don't know, in terms of forecasting or prognosticating or whatever. Do we have an idea that this is gonna? I thought I saw something that said we're gonna have a snowier, icier, or something winter for the upper Midwest and including Wisconsin.
I think one of the factors that can turn us the other way is whether or not a strong El Nino is ongoing in the late summer and early fall. And it doesn't seem that that's the case. And an El Nino is a situation, it's an atmosphere ocean combination disturbance that somehow drags warm water to the central equatorial Pacific. And when that happens, that's where all the thunderstorm activity gets displaced to that location. And thunderstorms at low latitudes have an impact on the jet stream, and the jet stream then has an impact on the types and paths of weather systems that come across the continental North America. So when there's an El Nino, when the tropical Pacific is warmer, the surface of the ocean is warmer than normal, that tends to make us warmer and wetter in the wintertime. That's a pretty solid signal. There's variation around it, but it's a pretty good bet that if there's a good El Nino going on, we won't get a traditional snowy winter. Right now, there's no such feature developing in the tropical Pacific. Now, the problem is the other side of the coin, the absence of an El Nino does not have as strong a signal. It doesn't have an opposite signal. So we don't know for sure that we're going to get a colder and snowier winter. I think for my money, I would say the only thing I can feel somewhat confident won't happen is we won't have a complete washout that is a result of an El Nino. You can still have a washout for other reasons, but it won't be because of that. And so that eliminates one thing that could disappoint me for the winter. And that encourages me that maybe we'll get something normal. The other thing is we haven't had a normal snowfall in about 3 straight winters total for the season. That's hard to sustain. So even in a global warming environment, winter is still winter in Wisconsin, and we can still depend on getting a couple of really exciting snow events. So I have hope that part of it scientific, the non-El Nino part, the other part just law of averages, sort of regression to the mean. We'll find ourselves back in something more like a normal winter this year because we haven't had one in a couple.
It sounds good to me. I'm going to strap on the snowshoes, I hope, this winter. And I think I'm going to get out there for a nice walk in this beautiful fall afternoon today.
Absolutely.
So
Yeah.
we're gonna leave it there, and we'll wrap things up. Thank you so much for being with us. We appreciate it.
Thank you for having me. I really appreciate that.
Jonathan Martin is a professor in the UW-Madison Department of Atmospheric and Oceanic Sciences. You can hear him on the Larry Mueller Show on the Ideas Network of Wisconsin Public Radio. Pretty sure that's the last Monday of each month.
That's correct. We're coming up Monday.
Yep. So yeah, it's Jonathan Martin and Steve Ackerman are the weather guys, heard on Wisconsin Public Radio the last Monday of each month at 11:45. Our next Plato lecture will be, what is critical race theory and why is it controversial? Our speaker will be UW-Madison Education Professor Emerita Gloria Ladson-Billings. That Zoom webinar lecture will be free and open to all, but please register at platomadison.org to get the link to join us on October 26th from 1:30 until 3 p.m. And please, while you're there, renew your Plato Madison membership or join Plato Madison at platomadison.org. For Plato Madison, I'm Joy Cardine. Thanks for being with us. I hope to see you next time.